Light, as we know it, is the fastest thing in the universe. It travels across space at an incredible speed of 299,792,458 meters per second in a vacuum. This cosmic speed limit has fascinated scientists for centuries, shaping our understanding of everything from the smallest particles to the largest galaxies. Light carries information across billions of years, connecting us to distant stars and revealing the secrets of the cosmos. It defines the very fabric of time itself, creating the framework within which all of reality unfolds. But tonight, we embark on a journey that challenges everything we think we know about light and its limitations. What if the speed of light, this fundamental constant that governs our universe, is not actually universal at all? What if it exists only within the boundaries of our own dimension, a local rule rather than a cosmic law? Imagine for a moment that beyond our familiar 3 dimensions of space and 1 dimension of time, there exist other realms where light behaves completely differently. In these mysterious dimensions, light might travel faster than we ever thought possible, or perhaps it might not exist at all in the way we understand it. This possibility opens up a universe of questions that stretch the very limits of human imagination. If the speed of light is bound to our dimension, what does that mean for our understanding of space, time, and reality itself? Could there be dimensions where information travels instantaneously, where the barriers that separate cause and effect simply do not exist? Could there be realms where the very concept of distance becomes meaningless because light, or whatever takes its place, connects all points in space without the delays we experience in our world? The implications are staggering. Every measurement we have made, every theory we have constructed, every law of physics we hold dear, might be nothing more than local phenomena, applicable only to the slice of reality we call home. The speed of light has been our cosmic measuring stick, the foundation upon which we built Einstein's theories of relativity, our understanding of black holes, and our calculations of the age and size of the universe. But what if this measuring stick only works in our own backyard? As we explore this fascinating possibility, we will journey through the cutting edge of theoretical physics, diving deep into concepts that challenge our most basic assumptions about reality. We will examine how the speed of light shapes everything we observe, from the gentle glow of starlight to the violent explosions of supernovas. We will investigate the mysterious world of higher dimensions, where mathematical equations suggest that reality extends far beyond what our senses can perceive. Tonight, we invite you to question everything you thought you knew about light, speed, and the nature of existence itself. We will explore worlds where the impossible becomes possible, where the speed of light is just one option among many, and where the universe reveals secrets that could transform our understanding of everything. So settle in, close your eyes, and prepare to embark on a journey through dimensions unknown, where light itself might be just the beginning of an even greater mystery. To understand why the speed of light might be unique to our dimension, we must first explore what makes this speed so special in our world. Light travels at exactly 299,792,458 meters per second through the vacuum of space. This number is not arbitrary. It represents one of the most fundamental constants in our universe, a speed limit that nothing with mass can ever reach, let alone exceed. When we look up at the night sky, we are witnessing the power of this cosmic speed limit in action. The light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years to reach us. The light from distant galaxies has been traveling for billions of years, carrying with it information about the universe as it existed long before Earth even formed. This delay, this cosmic lag time, shapes everything we know about space and time. Albert Einstein revolutionized our understanding of reality when he proposed that the speed of light is absolute. Unlike other speeds we encounter in daily life, the speed of light never changes, regardless of who measures it or how fast they are moving. If you shine a flashlight while running, the light does not travel faster than if you were standing still. This strange behavior led Einstein to realize that space and time themselves must be flexible, stretching and compressing to keep the speed of light constant. This insight gave birth to the theory of special relativity in 1905, forever changing how we think about the universe. Einstein showed us that time itself slows down as objects approach the speed of light. A spacecraft traveling at 99% of light speed would experience time much more slowly than we do on Earth. What feels like a year to the travelers might be equivalent to 7 years on Earth. This time dilation effect has been confirmed countless times through experiments with atomic clocks and high-speed particles. The speed of light also determines the relationship between energy and matter through Einstein's famous equation E equals mc squared. This simple formula tells us that matter and energy are two forms of the same thing, and the speed of light squared is the conversion factor between them. Every atom in your body contains enormous amounts of energy, locked away by this fundamental relationship. The sun converts 4 million tons of matter into pure energy every second, following this exact principle. But perhaps most remarkably, the speed of light creates what physicists call the light cone, a boundary that determines what events can influence each other. Imagine you are standing at the center of an expanding sphere of light. Everything inside this sphere represents events that could potentially affect you, while everything outside remains causally disconnected. This means that right now, there are countless events happening throughout the universe that cannot influence you simply because the light carrying information about them has not had enough time to reach you. The speed of light also sets the ultimate limit for how fast information can travel. No signal, no message, no influence can travel faster than light in our dimension. This creates a fundamental loneliness in the universe, separating distant regions of space from immediate communication. When we observe a supernova explosion in a distant galaxy, we know that this magnificent event happened millions of years ago, but there is no way to send a message to that galaxy and receive a reply within a human lifetime. This speed limit has profound implications for the structure of space and time itself. Space and time are not separate entities, but form a unified fabric called space-time. The speed of light determines the geometry of this fabric, setting the rate at which time flows relative to the dimensions of space. In our dimension, 1 second of time corresponds to light traveling about 300 million meters through space. This relationship between space and time creates the four-dimensional stage upon which all physical events unfold. The constancy of light speed has allowed us to make incredibly precise measurements of the universe. We can determine the distance to galaxies billions of light years away, calculate the age of the universe at 13.8 billion years, and predict the behavior of black holes, whose gravity is so strong that not even light can escape. All of these achievements depend on the assumption that the speed of light is truly constant throughout space and time. Yet as we probe deeper into the mysteries of physics, questions begin to emerge. The speed of light seems perfectly tuned for our universe. But why this speed and not another? What determines this particular value? Could it be that this speed is not a fundamental property of reality itself, but rather a characteristic of the specific dimensional space we inhabit? These questions lead us to wonder whether the speed of light, which seems so absolute and unchanging in our experience, might actually be just one possibility among many in a vast multiverse of different physical laws. Throughout history, measuring the speed of light has been one of humanity's greatest scientific challenges. Early attempts by Galileo using lanterns and hilltops failed because light travels far too quickly for human reflexes to detect. It wasn't until 1676 that Ole Rømer made the first successful measurement by observing the moons of Jupiter. He noticed that the timing of eclipses seemed to vary depending on Earth's position in its orbit around the Sun. When Earth was farther from Jupiter, the eclipses appeared to happen later than predicted. Rømer realized this delay was caused by light taking extra time to travel the additional distance. This breakthrough revealed that light, despite appearing instantaneous to our everyday experience, actually takes time to travel from one place to another. Over the following centuries, scientists refined their measurements using increasingly sophisticated methods. They used rotating mirrors, interferometers, and eventually laser technology to pin down light's speed with extraordinary precision. Today, We know the speed of light to 15 decimal places, making it one of the most precisely measured constants in all of physics. But this precision raises profound questions about the nature of reality itself. Why does light travel at exactly this speed and not faster or slower? What would happen to our universe if light moved at a different pace? These are not merely academic questions. The speed of light is woven so deeply into the fabric of our reality that changing it would fundamentally alter everything we know about existence. Consider what would happen if light traveled just twice as fast in our dimension. Time dilation effects would be reduced, making high-speed space travel less exotic. The energy locked in matter through E=mc² would be 4 times greater, making atomic reactions incredibly more powerful. Stars would burn differently, planets would receive energy at different rates, and the delicate balance that allows life to exist might be completely disrupted. The universe would be a radically different place. Conversely, if light traveled much slower, say at the speed of sound, our world would become a strange place indeed. We would see lightning strikes minutes after they occurred. The sun would appear to flicker and dance as light from different parts of its surface arrived at different times. Radio signals would crawl across the globe, making instant communication impossible. The night sky would become a shifting tapestry of delayed images, with nearby stars appearing to move in slow motion relative to distant ones. The speed of light also determines the strength of electromagnetic forces that hold atoms together. Light is, after all, simply electromagnetic radiation that our eyes can detect. The same force that creates light also binds electrons to atomic nuclei, holds molecules together, and generates the magnetic fields that protect Earth from harmful cosmic radiation. If light traveled at a different speed, these fundamental forces would change, potentially making complex chemistry and biology impossible. In our dimension, the speed of light creates what physicists call the fine structure constant, a number that describes the strength of electromagnetic interactions. This constant appears to be perfectly tuned to allow for the existence of stable atoms, complex molecules, and ultimately life itself. Even tiny changes to this value would prevent stars from forming, atoms from binding, or chemical reactions from occurring in the ways necessary for biological processes. The speed of light also sets the scale for quantum mechanics, the strange world of subatomic particles where probability replaces certainty, and particles can exist in multiple states simultaneously. At the quantum level, the speed of light determines how quickly information can be exchanged between particles, how fast quantum states can change, and how energy and momentum are related. Without this specific speed, the quantum world might operate according to completely different rules, changing the fundamental building blocks of matter and energy. Perhaps most mysteriously, the speed of light appears to be connected to the geometry of space itself. In our three-dimensional world plus time, the speed of light defines the relationship between spatial distances and temporal intervals. This relationship creates what mathematicians call Minkowski spacetime, a four-dimensional arena where all physical events take place. The speed of light essentially tells us how to convert between measurements of space and measurements of time, creating a unified framework for understanding motion, gravity, and the expansion of the universe. This geometric role of light speed becomes even more intriguing when we consider that our familiar three dimensions of space might not be the whole story. Modern physics suggests that additional dimensions could exist beyond our direct perception, folded up or hidden in ways that make them invisible to our everyday experience. If these extra dimensions exist, they might have their own characteristic speeds, their own relationships between space and time, and their own versions of what we call the speed of light. The cosmic microwave background radiation that fills our universe provides another window into the fundamental nature of light speed. This ancient light, released when the universe was only 380,000 years old, has been traveling through space for over 13 billion years. Throughout this incredible journey, it has maintained the same speed, suggesting that light's velocity has remained constant across vast distances and enormous spans of time. Yet this constancy applies only to our observable universe, the region of space from which light has had time to reach us since the Big Bang. Beyond this cosmic horizon lies the great unknown, regions of space that remain forever hidden from our view because their light has not yet had time to reach us, and perhaps never will due to the expansion of space itself. In these distant realms, we cannot directly verify that light behaves the same way it does in our local region of the universe. We assume it does, but this assumption might be nothing more than the bias of creatures who have evolved in a single, specific type of dimensional environment. The speed of light in our dimension seems to govern everything from the flow of time to the distance between stars. But is it an absolute law, or is it simply a feature of our own reality? We live in a universe of 3 dimensions of space and 1 of time. This might seem like an obvious statement, but it represents one of the most profound limitations of human experience. We move forward and backward, left and right, up and down, and we experience the forward flow of time. These 4 dimensions define the boundaries of everything we can directly perceive, touch, and measure. Yet modern physics suggests that reality extends far beyond these familiar boundaries, into realms where entirely different rules might apply. The concept of extra dimensions first emerged from the mathematical equations that describe the fundamental forces of nature. When physicists attempt to unify gravity with the other forces of physics, they consistently find that their equations work best when they include additional spatial dimensions beyond the 3 we experience. These are not merely mathematical curiosities, but appear to be essential features of reality itself, hidden from our direct observation, but influencing the behavior of everything around us. Imagine trying to explain our 3-dimensional world to a creature that lived on a flat, 2-dimensional surface. This hypothetical being could move forward and backward, left and right, but would have no concept of up and down. From its perspective, our 3rd dimension would be completely invisible and incomprehensible. When we pass through its flat world, it might see only a cross-section of our 3-dimensional form, never grasping the full reality of our existence. We might be in exactly the same situation, creatures of limited dimensional perception trying to understand a reality that extends into realms we cannot directly access. The mathematics of string theory suggests that our universe actually contains 10 or 11 dimensions in total. 6 or 7 of these extra dimensions are thought to be compactified, meaning they are curled up so tightly at every point in space that they remain invisible to our largest particle accelerators and most sensitive instruments. These hidden dimensions might be smaller than the smallest subatomic particles, yet they could fundamentally influence the behavior of everything in our observable universe. Think of it this way: if you look at a garden hose from far away, it appears to be a one-dimensional line. Only when you get closer do you realize that it actually has width and depth, additional dimensions that were hidden by your limited perspective. The extra dimensions of space might be similar, present everywhere around us, but invisible because they exist on scales far smaller than anything we can currently detect. But what if these extra dimensions are not just mathematical abstractions? What if they represent actual spaces where the laws of physics operate differently than they do in our familiar 3-dimensional realm? In these hidden dimensions, the speed of light might not be the cosmic speed limit we know. It might be faster, slower, or perhaps light, as we understand it, might not exist at all. Consider the possibility that each dimension has its own characteristic velocity, its own version of what we call the speed of light. In our 3-dimensional space, this speed happens to be about 300 million meters per second, but in a 4th spatial dimension, this characteristic speed might be entirely different. Information and energy might flow through 4th dimensional space at rates that would seem impossible from our limited perspective. The concept becomes even more intriguing when we consider that these extra dimensions might not be compactified everywhere. There could be regions of the universe, perhaps in the space between galaxies or in the cores of black holes, where these additional dimensions open up and become accessible. In such regions, the rules of physics as we know them might break down completely. Light might behave in ways that violate everything we think we know about the nature of reality. Some theories suggest that our entire universe might be a 3-dimensional surface, called a brane, floating in a higher dimensional space called the bulk. From this perspective, we are like creatures living on the surface of a soap bubble, unable to perceive the 3-dimensional space that surrounds our bubble. All the forces we experience, all the particles we can detect, all the light we can observe, might be trapped on our 3-dimensional brane, while gravity alone has the ability to leak into the extra dimensions of the bulk. If this picture is correct, then the speed of light might be nothing more than a local property of our particular brane. Other branes floating in the same higher dimensional space might have completely different speed limits, different relationships between space and time, and different fundamental constants. What we consider to be universal laws might be as local and specific as the weather patterns on Earth. The implications of this possibility stretch far beyond abstract physics. If other dimensions exist where light travels faster than it does in our space, then the barriers that separate distant regions of our universe might not exist in those realms. Information could flow instantaneously across what we perceive as vast cosmic distances. Events that seem causally disconnected in our dimension might be intimately connected through pathways that exist in higher dimensional space. This could explain some of the most puzzling aspects of quantum mechanics, where particles seem to influence each other instantaneously across arbitrary distances. What appears to be faster than light communication in our dimension might actually be normal, slower than light communication taking place through extra dimensions where different speed limits apply. The particles are not violating the speed of light in those hidden dimensions. They are simply using pathways that are invisible to our three-dimensional perspective. The cosmic inflation that occurred in the first moments after the Big Bang might also be understood differently if extra dimensions exist. The rapid expansion of space itself, which appears to have proceeded faster than light from our perspective, might have been driven by processes occurring in higher dimensional space, where such speeds are perfectly normal. Our universe might have inflated by borrowing energy and momentum from dimensions we cannot directly observe. Dark matter and dark energy, the mysterious substances that make up 95% of our universe, might also be manifestations of extra-dimensional physics. These invisible components of reality could be ordinary matter and energy, existing primarily in dimensions beyond our perception, influencing our three-dimensional space through gravitational effects while remaining otherwise undetectable. What we call dark might simply be hidden in dimensions where light, as we know it, cannot travel. Even more remarkably, the extra dimensions might not be static. They could be dynamic, changing over time, expanding and contracting in ways that influence the apparent constants of physics in our observable universe. The speed of light itself might be slowly changing as these hidden dimensions evolve, creating subtle variations that we have not yet learned to detect. What we measure as a constant might actually be a slowly varying parameter, locked to the geometry of dimensions beyond our direct experience. The possibility of multiple dimensions also raises profound questions about the nature of consciousness and observation. If reality extends into realms we cannot perceive, then our understanding of existence might be fundamentally incomplete. We might be like shadows cast by higher dimensional beings, experiencing only a limited projection of a much richer and more complex reality. Our measurements of the speed of light, our observations of space and time, might capture only a tiny fragment of the true nature of existence. Some theories even suggest that consciousness itself might be a higher dimensional phenomenon, capable of accessing information from beyond our three-dimensional space. This could explain the strange sense of intuition, the feeling that we sometimes know things we have no logical reason to know, the mysterious connections that seem to exist between minds separated by vast distances. Perhaps consciousness operates in dimensions where information travels faster than light in our space, creating connections that seem impossible from our limited dimensional perspective. The search for extra dimensions has become one of the most active areas of experimental physics. Particle accelerators probe the smallest scales of space and time, looking for signs that energy is leaking into hidden dimensions. Astronomers study the cosmic microwave background radiation for subtle patterns that might reveal the influence of extra-dimensional space. Gravitational wave detectors listen for ripples in space-time that might carry signatures of higher dimensional physics. Yet, despite these efforts, the extra dimensions remain tantalizingly beyond our reach. This might be because they are truly compactified and inaccessible, or it might be because we have not yet developed the tools and techniques needed to explore them. Perhaps the speed of light in our dimension is precisely what prevents us from directly accessing these other realms, creating a kind of dimensional barrier that keeps us locked in our familiar three-dimensional prison. But what if the true nature of the cosmos extends beyond these limits, into realms where different rules might apply? In dimensions beyond our own, the forces we understand might operate in unfamiliar ways, and light might no longer be bound by the speed we know. To understand this possibility, we must first examine how the fundamental forces of nature might behave when they are no longer confined to our familiar three-dimensional space. Gravity, the weakest of the four fundamental forces in our dimension, provides our first clue about how physics might change in higher dimensional spaces. Unlike the other forces, gravity seems to dilute more rapidly with distance than we would expect in a purely three-dimensional universe. When we measure gravitational strength at very small scales, using sensitive instruments that can detect forces between microscopic objects, we find hints that gravity might be leaking into extra dimensions, spreading its influence across spaces we cannot directly perceive. In our three-dimensional world, the strength of gravity decreases with the square of distance. Double the distance between two objects, and the gravitational force becomes 4 times weaker. This inverse square law has been tested countless times and holds true for all the distances we can measure, from laboratory experiments to the orbits of planets around stars. But what if this law only applies within our dimensional limitations? In higher dimensional spaces, gravity might follow different rules entirely. Instead of decreasing with the square of distance, it might diminute with the cube, 4th power, or even higher powers of distance, depending on how many extra dimensions exist and how they are structured. This means that at very small scales, where extra dimensions might become accessible, gravity could be far stronger than we observe in our everyday three-dimensional experience. This possibility has profound implications for our understanding of why gravity is so much weaker than the other fundamental forces. In our dimension, gravity is about 10 to the 36th times weaker than electromagnetism. This enormous difference has puzzled physicists for decades. Why should one fundamental force be so incredibly feeble compared to the others? The answer might be that gravity is not actually weak at all. Instead, it might be a strong force that appears weak, because most of its strength is spreading into dimensions we cannot access. If gravity behaves differently in higher dimensions, then electromagnetic forces, which give rise to light, might also follow different rules in those realms. The speed of light is intimately connected to the strength of electromagnetic interactions. Change the fundamental properties of electromagnetism, and you automatically change how fast light can travel through space. In our dimension, light propagates through electromagnetic fields that permeate all of space. These fields have specific properties that determine exactly how fast electromagnetic waves can travel. The speed of light is essentially the speed at which changes in these fields can propagate from one location to another. But in higher dimensions, the structure of electromagnetic fields might be completely different. Imagine electromagnetic fields that exist in 4, 5, or 6 spatial dimensions instead of our familiar 3. These higher dimensional fields might support electromagnetic waves that travel at speeds far exceeding our cosmic speed limit. What we perceive as the ultimate speed barrier might be nothing more than a limitation imposed by the three-dimensional structure of the electromagnetic fields in our local region of reality. The mathematical equations that describe electromagnetism, known as Maxwell's equations, were originally formulated for three-dimensional space. When physicists extend these equations to higher dimensions, they find that the solutions can support electromagnetic waves with properties that seem impossible from our limited perspective. These waves might carry energy and information at speeds that would violate every principle of relativity as we understand it. But perhaps even more intriguingly, higher dimensional electromagnetic fields might support entirely new types of waves that have no analog in our three-dimensional experience. Just as our three-dimensional space supports both electric and magnetic fields that combine to create light, higher dimensional spaces might contain additional field components that interact in ways we cannot currently imagine. These exotic field configurations might be capable of transmitting information instantaneously across arbitrary distances, or they might create connections between distant regions of space that appear unrelated from our three-dimensional viewpoint. The strong nuclear force, which holds the protons and neutrons together in atomic nuclei, might also behave radically differently in higher dimensions. In our three-dimensional world, this force operates only over extremely short distances, confining quarks within protons and neutrons and binding these particles together to form atomic nuclei. But in higher dimensional space, the strong force might have a much longer range, potentially connecting particles across distances that seem impossibly large from our perspective. If the strong force can reach across higher dimensions, then particles that appear to be separated by vast distances in our three-dimensional space might actually be in direct contact through pathways that exist in extra dimensions. This could explain the strange phenomenon of quantum entanglement, where particles seem to share information instantaneously regardless of the distance separating them. Rather than representing a violation of the speed of light, quantum entanglement might simply be the result of particles maintaining contact through dimensions we cannot perceive. The weak nuclear force, responsible for certain types of radioactive decay, might also be transformed in higher dimensional space. In our dimension, weak interactions occur through the exchange of massive particles, called W and Z bosons. These particles are so heavy that they can only travel very short distances before decaying, which is why the weak force has such a limited range. But in higher dimensions, there might exist lighter versions of these particles, or entirely new particles that can carry weak interactions across much larger distances. Perhaps most remarkably, higher dimensions might support forces that have no counterpart in our three-dimensional experience. Just as a two-dimensional being would be unable to comprehend magnetic forces, which require three-dimensional space to manifest their full complexity, we might be blind to fundamental forces that operate primarily in higher dimensional realms. These unknown forces might be responsible for phenomena we currently attribute to dark matter and dark energy, the mysterious components of our universe that seem to influence cosmic evolution without interacting directly with ordinary matter and light. The concept of symmetry, which plays a central role in our understanding of fundamental physics, might also be dramatically different in higher dimensions. In our three-dimensional world, the laws of physics exhibit certain symmetries that determine which interactions are possible and which are forbidden. Rotate a physics experiment, and the results remain the same. Reflect it in a mirror, and most processes proceed identically. But higher dimensions might possess symmetries that have no analog in our experience, leading to physical laws that seem to violate everything we think we know about cause and effect. These higher dimensional symmetries might allow for interactions that appear to violate conservation of energy, momentum, and even causality from our three-dimensional perspective. Energy might flow from our dimension into higher dimensional space, or it might spontaneously appear in our world as it flows down from dimensions we cannot access. Particles might seem to accelerate without any apparent force acting on them, driven by influences that originate in realms beyond our perception. The concept of distance itself might be fundamentally different in higher dimensions. In our three-dimensional space, the shortest path between 2 points is always a straight line. But in higher dimensional space, there might be shortcuts that allow for travel between distant locations without crossing the intervening space in our dimension. What appears to be faster than light travel might actually be normal, slower than light travel taking place along paths that are invisible to our three-dimensional viewpoint. Time, too, might behave differently in higher dimensions. We experience time as a single dimension that flows uniformly from past to future. But higher dimensional theories suggest the possibility of multiple time dimensions, or time dimensions that are twisted and curved in ways that allow for connections between different moments. In such realms, the relationship between cause and effect might be far more complex than we can imagine from our limited temporal perspective. The temperature and density of space itself might also be different in higher dimensions. Our three-dimensional space has an average temperature of about 3 degrees above absolute zero, set by the cosmic microwave background radiation left over from the Big Bang. But higher dimensional space might be much hotter or colder, influencing the behavior of particles and fields in ways that affect how light and other forms of energy propagate. Particle physics experiments have already begun to probe some of these possibilities. When high-energy particles collide in accelerators like the Large Hadron Collider, they occasionally produce results that seem to violate conservation of energy and momentum. Some of this missing energy might be escaping into extra dimensions, carried by particles that can access higher dimensional space while remaining invisible to our three-dimensional detectors. The implications extend far beyond abstract physics. If different physical laws operate in higher dimensions, then the apparent constants of nature that we measure in our three-dimensional world might actually be variable quantities that depend on the structure and dynamics of extra-dimensional space. The speed of light, the strength of gravity, the masses of fundamental particles, all of these might be slowly changing as higher dimensions evolve and interact with our familiar three-dimensional realm. This possibility suggests that our universe might be far more dynamic and interconnected than we currently realize. What we perceive as separate and distinct regions of space might be intimately connected through networks of higher dimensional interactions. The light from distant stars might be influenced by processes occurring in dimensions we cannot detect. The evolution of galaxies might be guided by forces that operate primarily beyond our three-dimensional perspective. Even the arrow of time itself might be different in higher dimensions. While we experience time as flowing inexorably from past to future, higher dimensional theories suggest that time might be more like space in extra dimensions, with the possibility of movement in multiple temporal directions. This could create connections between different moments in our timeline, allowing for influences that seem to violate causality from our limited perspective. The quantum vacuum, the seething sea of virtual particles that fills all of empty space in our dimension, might also be different in higher dimensional realms. These virtual particles constantly appear and disappear, borrowing energy from the uncertainty principle and returning it before they can be directly detected. But in higher dimensions, virtual particles might have different properties, different lifetimes, and different ways of interacting with the particles and fields we can observe. Some theories suggest that consciousness itself might be sensitive to higher dimensional physics, capable of detecting influences and information that our scientific instruments cannot measure. This could explain phenomena like intuition, creativity, and the strange sense of connection that people sometimes feel across great distances. Perhaps the human brain, with its complex network of neural connections, is actually a higher dimensional information processing system that can access data from realms beyond our three-dimensional space. As we continue to probe the boundaries of physics, searching for signs of extra dimensions and testing the limits of our current theories, we edge closer to understanding whether the speed of light is truly universal or merely a local property of our particular dimensional environment. The answer to this question could transform our understanding of reality itself, opening doorways to realms where light, space, time, and matter behave in ways that challenge everything we thought we knew about the nature of existence. In dimensions beyond our reach, the forces we understand might operate in unfamiliar ways, creating a cosmos far stranger and more wonderful than we have yet dared to imagine. In our universe, light not only illuminates the world around us, but it defines the very structure of reality. To truly understand why the speed of light might be unique to our dimension, we must first appreciate the extraordinary role that light plays in shaping everything from the smallest atoms to the largest structures in the cosmos. Light is far more than just the phenomenon that allows us to see. It is the fundamental messenger of the universe, the carrier of information, and the thread that weaves together the fabric of space and time itself. When we look around us, everything we perceive is the result of light interacting with matter. The colors we see are specific frequencies of electromagnetic radiation absorbed and reflected by different materials. The warmth we feel from the sun is infrared light carrying energy across 93 million miles of empty space. The radio waves that bring us music and communication are simply light at frequencies our eyes cannot detect. X-rays that reveal the inner structure of our bodies, microwaves that heat our food, ultraviolet radiation that can burn our skin, all of these are manifestations of the same fundamental phenomenon, operating at different frequencies. This electromagnetic spectrum spans an enormous range, from radio waves with wavelengths longer than football fields, to gamma rays with wavelengths smaller than atomic nuclei. Yet all of these different types of radiation travel at exactly the same speed through empty space. This universality of light speed across all electromagnetic frequencies provides one of the strongest pieces of evidence that the speed of light represents a fundamental property of space and time, rather than a characteristic of any particular type of wave or particle. The interaction between light and matter follows precise mathematical laws that have remained constant throughout the observable history of our universe. When light encounters an atom, it can be absorbed, reflected, or transmitted, depending on the energy of the light and the electronic structure of the atom. These interactions are so precisely determined that we can identify the chemical composition of distant stars by analyzing the specific frequencies of light they absorb and emit. The fact that these atomic fingerprints remain consistent across billions of years and trillions of miles suggests that the fundamental relationship between light and matter has not changed since the early universe. But light does far more than simply interact with existing matter. In many ways, light creates the very possibility of complex structures in our universe. The electromagnetic force that gives rise to light is the same force that holds electrons in orbit around atomic nuclei, bonds atoms together to form molecules, and enables the chemical reactions that power all biological processes. Without electromagnetic interactions, atoms could not form stable structures, molecules could not exist, and life as we know it would be impossible. The Sun, our nearest star, converts 4 million tons of matter into pure energy every second through nuclear fusion reactions. This energy emerges as light that travels through space to power virtually every process on Earth. Plants capture sunlight and convert it into chemical energy through photosynthesis, forming the base of all food chains. Weather patterns are driven by solar heating that creates wind, rain, and ocean currents. Even fossil fuels represent ancient sunlight stored in the chemical bonds of organic molecules that formed millions of years ago. This intimate connection between light and life suggests that the speed of light in our dimension is not arbitrary but precisely tuned to enable the complex processes necessary for biological evolution. If light traveled much faster, the energy delivery from stars might be too intense for delicate organic molecules to survive. If light traveled much slower, the energy transfer might be too weak to drive the chemical reactions necessary for metabolism and growth. Light also serves as the universe's ultimate information carrier. Every measurement we make about distant objects, every observation that extends our knowledge beyond our immediate vicinity, depends on light traveling from those objects to our instruments. The cosmic microwave background radiation carries information about the universe when it was only 380,000 years old. Light from distant galaxies tells us about cosmic evolution over billions of years. Even our understanding of nearby objects like planets and asteroids comes primarily through analysis of reflected and emitted light. This informational role of light creates a fundamental connection between knowledge and the speed of light. In our dimension, information cannot travel faster than light, which means that all knowledge about distant events must wait for light to carry that information across space. This creates what physicists call the light cone of causality, a boundary that determines which events can influence each other and which remain forever disconnected. The behavior of light in our universe also reveals the deep connection between electricity and magnetism that was first discovered by James Clerk Maxwell in the 1860s. Maxwell's equations showed that light is an electromagnetic wave, a self-propagating disturbance in electric and magnetic fields that can travel through empty space. This discovery unified two forces that had previously seemed completely separate and revealed that light, electricity, and magnetism are different aspects of a single fundamental force. This electromagnetic unification has profound implications for our understanding of how light might behave in other dimensions. If the structure of electric and magnetic fields is different in higher dimensional space, then light itself might have properties that seem impossible from our three-dimensional perspective. Higher dimensional light might carry more information, travel at different speeds, or interact with matter in ways that violate everything we think we know about electromagnetic radiation. The quantum nature of light adds another layer of complexity to its role in our universe. Light exhibits wave-particle duality, behaving sometimes like a continuous wave and sometimes like discrete particles called photons. This dual nature is not merely a theoretical curiosity, but has practical consequences for how light interacts with matter at the smallest scales. When light hits a solar cell, it transfers energy in discrete quantum packets. When it passes through optical instruments, it interferes with itself like a wave. This quantum behavior of light is essential for many modern technologies, from lasers to quantum computers. In our dimension, the quantum properties of light are precisely determined by the relationship between energy and frequency given by Planck's constant. This fundamental constant sets the scale for all quantum mechanical effects and determines how matter and energy interact at the smallest scales. But in other dimensions, the quantum properties of light might be governed by different constants, leading to entirely different relationships between energy, frequency, and the speed of propagation. The interaction between light and gravity, predicted by Einstein's general theory of relativity, provides yet another window into the fundamental nature of space and time. Light bends when it passes near massive objects, not because photons have mass, but because mass and energy curve the geometry of space-time itself. This gravitational lensing effect has been observed countless times, from the bending of starlight during solar eclipses to the magnification of distant galaxies by intervening galaxy clusters. The fact that light follows the curvature of space-time suggests that the speed of light is intimately connected to the geometry of our dimension. In regions where gravity is strong, time itself runs slower, but light always travels at the same local speed relative to local clocks and rulers. This constancy of light speed in all reference frames is what led Einstein to realize that space and time must be flexible, adjusting themselves to preserve the fundamental relationship between light, space, and time. But what if this relationship only holds in our particular dimensional configuration? In higher dimensional space, where gravity might behave very differently, the interaction between light and space-time curvature might follow entirely different rules. Light might be able to take shortcuts through higher dimensions, traveling between distant points without following the curved paths required in our three-dimensional space. The polarization of light provides another clue about its fundamental nature in our dimension. Light waves oscillate in directions perpendicular to their direction of travel, and these oscillations can be oriented in specific patterns called polarizations. In our three-dimensional space, light can be polarized in two independent directions, but in higher dimensional space, light might support additional polarization states that have no analog in our experience. These extra polarization modes could carry information in ways that seem impossible from our three-dimensional perspective. They might enable forms of communication that appear to violate the normal limitations of electromagnetic radiation, or they might reveal the presence of fields and forces that remain invisible to our current instruments. The spectrum of light emitted by different astronomical objects tells us about the physical conditions in some of the most extreme environments in the universe. The light from neutron stars reveals matter compressed to nuclear density. The radiation from black hole accretion disks shows us matter heated to billions of degrees. The cosmic microwave background carries the thermal signature of the entire observable universe when it was young and hot. All of these observations depend on the assumption that light behaves the same way throughout space and time. But what if this assumption is wrong? What if light in extreme environments, where the curvature of space-time approaches the limits of our current theories, begins to show signs of higher dimensional behavior? Recent observations of gamma-ray bursts, the most energetic explosions in the universe, have revealed hints that the speed of light might vary slightly at the highest energies, suggesting that our understanding of electromagnetic radiation might be incomplete. The role of light in biological vision reveals another aspect of its fundamental importance in our dimension. The evolution of eyes represents one of the most remarkable achievements of natural selection, creating organs capable of detecting and processing electromagnetic radiation with extraordinary sensitivity and precision. Some animals can see individual photons, while others can detect polarization patterns invisible to human eyes. The fact that life has evolved such sophisticated mechanisms for detecting light suggests that electromagnetic radiation plays a crucial role in the flow of information that drives biological evolution. But vision is just one way that living organisms interact with light. Many creatures use bioluminescence to create their own light for communication, defense, or hunting. Plants use specialized molecules to capture specific frequencies of light for photosynthesis. Some bacteria can even use light as a source of energy through photosynthetic processes that differ from those found in plants. These biological interactions with light have evolved over billions of years, fine-tuning themselves to the specific properties of electromagnetic radiation in our dimension. If light behaved differently in our universe, if it traveled at a different speed or had different quantum properties, life might have evolved along completely different pathways, or it might not have evolved at all. The technological applications of light in human civilization demonstrate our growing ability to manipulate and control electromagnetic radiation for practical purposes. Lasers concentrate light into intense, coherent beams that can cut through metal, perform delicate surgery, or carry information across continents through optical fibers. Light-emitting diodes convert electrical energy into light with remarkable efficiency, enabling everything from smartphone displays to large-scale architectural lighting. These technologies depend on our precise understanding of how light behaves in our dimension. They work because we can predict exactly how light will interact with different materials, how it will propagate through various media, and how it will respond to electric and magnetic fields. But if light in other dimensions behaves according to different rules, then entirely new technologies might be possible, technologies that seem to violate the fundamental limitations we observe in our three-dimensional world. The study of how light propagates through different materials has revealed deep insights into the structure of matter itself. When light passes through crystals, glasses, or other transparent substances, its speed decreases in a way that depends on the density and arrangement of atoms in the material. This change in light speed, characterized by the refractive index, determines how lenses focus light and how optical instruments form images. The fact that light slows down in matter but always returns to the same speed when it emerges back into vacuum suggests that the speed of light in empty space represents a fundamental property of the dimensional structure itself rather than a characteristic of any particular substance. In other dimensions, where the structure of empty space might be different, this fundamental speed might have entirely different values. In our universe, light not only illuminates the world around us, but it defines the very structure of reality, serving as the bridge between our universe and the information we gather about it. But could this be different in another dimension, where the rules we know don't apply? Space-time is a flexible fabric in our universe, but could its very essence change in dimensions beyond our reach? What if light was simply a product of our limited perception of reality? To understand these profound questions, we must examine how the fundamental nature of space and time themselves might be transformed in higher dimensional realms, and how these changes could completely alter the role that light plays in the structure of existence. In our familiar three-dimensional world plus time, space and time are woven together into a unified fabric that Einstein called space-time. This four-dimensional arena provides the stage upon which all physical events unfold. The geometry of this space-time fabric determines how objects move, how forces propagate, and crucially, how fast light can travel from one location to another. But this four-dimensional structure might represent only a tiny slice of a much larger and more complex reality. When mathematicians and physicists extend their equations to include additional spatial dimensions, they discover that the relationship between space and time becomes far more intricate and flexible than anything we experience in our everyday lives. In higher dimensional theories, time itself might not be unique. There could be multiple time directions, each flowing at different rates and potentially in different directions. What we experience as the single, inexorable flow of time from past to future might be just one thread in a complex temporal tapestry that extends through dimensions we cannot perceive. Consider the implications of multiple time dimensions for the behavior of light. In our world, light travels through space over time, requiring specific durations to cover particular distances. But in a reality with multiple time dimensions, light might have access to temporal shortcuts that allow it to arrive at destinations before it appears to have left its starting point from our limited four-dimensional perspective. Events that seem to violate causality in our dimension might be perfectly normal when viewed from the broader context of higher dimensional spacetime. The curvature of spacetime, which we experience as gravity, might also behave very differently in higher dimensions. Einstein showed us that massive objects bend the fabric of spacetime, creating what we perceive as gravitational attraction. But in dimensions beyond our own, spacetime might curve in ways that have no analog in our four-dimensional experience. These exotic curvatures could create pathways through which light and other forms of energy could travel at speeds that seem impossible from our perspective. Imagine spacetime folded and twisted through higher dimensions like an origami sculpture existing in three-dimensional space. From our four-dimensional viewpoint, we might only see small sections of this complex structure, missing the connections and shortcuts that exist in the fuller reality. Light traveling along these higher dimensional pathways might appear to move faster than our cosmic speed limit, not because it actually exceeds the speed of light in its local frame of reference, but because it has access to routes through space-time that we cannot see or measure. The concept of distance itself becomes profoundly different in higher dimensional space. In our three-dimensional world, the shortest path between 2 points is always a straight line, and the distance between objects can be calculated using the familiar Pythagorean theorem. But when additional spatial dimensions are included, the geometry becomes much more complex. Points that appear far apart in our three-dimensional space might actually be very close together when measured through higher dimensional pathways. This could explain some of the most puzzling observations in modern cosmology. The cosmic microwave background radiation appears remarkably uniform across the entire sky, suggesting that distant regions of the universe that seem causally disconnected somehow managed to reach the same temperature in the early universe. This horizon problem has led cosmologists to propose cosmic inflation, a period of rapid expansion that supposedly brought these distant regions into contact before they were separated by the expansion of space. But what if the explanation is simpler? What if these apparently distant regions are actually in close contact through higher dimensional pathways that allow light and energy to flow between them at speeds that seem impossible from our four-dimensional perspective? The uniformity of the cosmic microwave background might not require exotic inflation mechanisms if the early universe had access to higher dimensional shortcuts that enabled rapid equilibration across vast distances. The expansion of the universe itself might be understood differently when viewed from a higher dimensional perspective. We observe that distant galaxies are moving away from us, with the most distant objects receding at speeds that approach or even exceed the speed of light. This observation led to the discovery that space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. But space expansion faster than light seems to violate the fundamental principle that nothing can exceed the speed of light. The resolution to this apparent contradiction is that the speed limit applies to objects moving through space, not to the expansion of space itself. However, this distinction might be artificial, a consequence of our limited four-dimensional perspective. In higher dimensions, what we interpret as space expansion might actually be motion along pathways that exist beyond our ability to perceive or measure. The dark energy that appears to be accelerating the expansion of the universe represents another mystery that might be resolved through higher dimensional physics. This invisible energy makes up about 70% of the total energy density of the universe, yet it interacts with ordinary matter only through its gravitational effects. Dark energy might not be a mysterious substance at all, but rather the manifestation of forces and fields that operate primarily in dimensions beyond our direct observation. If dark energy originates in higher dimensions, then its effects on the expansion of space might be accompanied by changes in the effective speed of light, as measured in our dimension. As higher dimensional fields evolve and interact, they might alter the local structure of space-time in ways that change the fundamental constants of physics, including the speed at which electromagnetic radiation can propagate. Time dilation, one of the most well-tested predictions of Einstein's relativity, might also work differently in higher dimensions. In our four-dimensional space-time, objects moving at high speeds or in strong gravitational fields experience time more slowly relative to stationary observers in weak gravitational fields. This effect has been measured countless times using atomic clocks on fast-moving aircraft and satellites orbiting Earth. But time dilation effects assume that time flows uniformly in all directions perpendicular to our three spatial dimensions. If additional time dimensions exist, then the relationship between motion, gravity, and the flow of time could be far more complex. Objects might experience different rates of time flow in different temporal directions, or they might have access to temporal pathways that allow them to influence their own past or future in ways that seem impossible from our limited perspective. The quantum mechanical properties of space and time might also be fundamentally different in higher dimensions. In our four-dimensional world, quantum field theory describes how particles and fields behave at the smallest scales of space and time. The uncertainty principle sets fundamental limits on how precisely we can measure position and momentum, energy and time. These quantum limitations appear to be built into the fabric of space-time itself. But in higher dimensions, the structure of quantum fields might support phenomena that have no analog in our experience. Virtual particles, which constantly appear and disappear in the quantum vacuum, might have longer lifetimes or different properties in extra-dimensional space. The uncertainty principle might operate differently, allowing for more precise measurements or creating new types of uncertainty that involve higher dimensional coordinates. These quantum effects in higher dimensions could influence the behavior of light in subtle but important ways. Photons might interact with virtual particles that exist primarily in extra-dimensional space, causing slight changes in their speed or direction that accumulate over cosmic distances. These interactions might explain some of the anomalies observed in high-precision measurements of light from distant sources. The topology of higher dimensional space, the way these dimensions are connected and shaped, could also have profound effects on the propagation of light and other forms of energy. In our three-dimensional space, topology is relatively simple. Space can be flat, curved, or twisted, but the basic connectivity remains straightforward. However, higher dimensional space might have extremely complex topologies, with regions that are connected in ways that seem impossible from our four-dimensional perspective. Imagine a higher dimensional space where what appears to be a single location in our three-dimensional world actually corresponds to multiple, widely separated regions in the full higher dimensional reality. Light entering such a region might split into multiple components that travel to different destinations, or it might be amplified or focused in ways that seem to violate conservation of energy from our limited viewpoint. Wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe, represent one type of exotic topology that might exist in higher dimensional space. While wormholes remain purely theoretical in our four-dimensional space-time, they might be natural features of higher dimensional reality. These passages could provide shortcuts for light and other forms of energy, allowing for apparent faster-than-light travel without actually violating local speed limits. The stability of these higher dimensional structures could also affect the apparent constants of physics in our observable universe. If extra dimensions are dynamic, expanding, contracting, or changing shape over cosmic time, then the effective speed of light in our dimension might vary slowly as these changes occur. What we measure as a fundamental constant might actually be a slowly evolving parameter that depends on the current state of dimensions we cannot directly observe. This possibility has led some physicists to propose that the fine structure constant, which determines the strength of electromagnetic interactions and is intimately related to the speed of light, might have been different in the early universe. Careful analysis of light from distant quasars has revealed hints that this fundamental constant might have changed slightly over the billions of years since that light was emitted. The dimensionality of space itself might not be fixed throughout the universe. Different regions of the cosmos might have access to different numbers of spatial dimensions, creating a patchwork reality where the laws of physics vary from place to place. In regions where extra dimensions are compactified and inaccessible, light might behave according to the rules we observe in our local environment. But in regions where extra dimensions open up and become accessible, light might exhibit properties that seem to violate everything we understand about electromagnetic radiation. The boundaries between regions of different dimensionality could create interfaces where light undergoes dramatic transformations. As electromagnetic radiation crosses from a four-dimensional region into a higher dimensional space, it might gain additional polarization modes, change its propagation speed, or interact with fields and particles that exist only in the extra dimensions. Black holes, the most extreme gravitational environments in our universe, might provide windows into higher dimensional physics. As matter falls toward a black hole, it experiences increasingly strong gravitational fields that curve space-time to its maximum extent. Near the event horizon, the boundary beyond which nothing can escape, the normal structure of space-time might break down, revealing the higher dimensional reality that lies beneath our four-dimensional perception. Recent theoretical work suggests that black holes might actually be higher dimensional objects that appear three-dimensional only because we observe them from our limited four-dimensional perspective. If this is correct, then the information that falls into black holes might not be destroyed but simply translated into higher dimensional forms that remain invisible to our current methods of observation. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, might reflect the projection of higher dimensional reality onto our four-dimensional space-time. From this perspective, everything we observe, including the speed of light and the structure of electromagnetic fields, might be holographic shadows cast by more fundamental processes occurring in higher dimensional space. The implications extend beyond physics into the realm of consciousness and perception. If reality is fundamentally higher dimensional, then our three-dimensional experience might be like watching shadows on the wall of Plato's cave, perceiving only projections of a richer and more complex existence. Our measurements of the speed of light, our observations of space and time, might capture only fragments of the true nature of reality. As we probe deeper into the mysteries of cosmology and particle physics, we find increasing evidence that our four-dimensional space-time is embedded in a larger structure that extends beyond our direct perception. The speed of light, which seems so fundamental and unchanging from our limited perspective, might be just one manifestation of deeper principles that govern the flow of information and energy through the full dimensionality of existence. Space-time is a flexible fabric in our universe, but in dimensions beyond our reach, its very essence might be transformed in ways that make our cosmic speed limit seem as arbitrary as the speed limit on a country road, a local restriction that has no meaning on the cosmic highways of higher dimensional space. If the speed of light is a boundary in our dimension, what lies beyond that boundary in other realms of reality? Could we one day unlock the secrets of faster-than-light travel through dimensions we have yet to understand? These questions strike at the heart of humanity's deepest aspirations for exploration and discovery, challenging us to imagine possibilities that extend far beyond the apparent limitations of our three-dimensional world. In our familiar space-time, Einstein's special theory of relativity establishes the speed of light as an absolute barrier. As objects with mass approach this cosmic speed limit, their energy requirements increase without bound, making it impossible to accelerate them to light speed using any finite amount of energy. This mathematical impossibility has led generations of physicists to conclude that faster-than-light travel is fundamentally impossible, at least within the framework of our current understanding of physics. But what if this prohibition exists only within the confines of our particular dimensional configuration? What if the energy barriers that prevent faster-than-light motion in our three-dimensional space simply do not exist in higher dimensional realms? The mathematical equations that describe motion in extra dimensions suggest possibilities that seem to violate everything we think we know about the limits of travel and communication. In higher dimensional space, the relationship between energy and velocity might follow completely different rules. While objects in our dimension require infinite energy to reach light speed, objects with access to extra dimensions might be able to achieve arbitrarily high velocities with finite energy inputs. This could happen if the extra dimensions provide alternative pathways for motion that bypass the energy barriers imposed by our three-dimensional space. Consider the analogy of an ant walking on the surface of a balloon. From the ant's two-dimensional perspective, traveling from one side of the balloon to the other requires a long journey across the curved surface. But if the ant could somehow access the third dimension, it could take a shortcut straight through the interior of the balloon, arriving at its destination in a fraction of the time required for surface travel. The ant would not violate any speed limits in the third dimension, but its journey would appear impossibly fast to other ants confined to the surface. Similarly, objects with access to higher dimensions might be able to take shortcuts through extra-dimensional space that allow them to traverse vast distances in our three-dimensional world without actually traveling faster than light in their local reference frame. These higher dimensional shortcuts could make interstellar travel practical on human timescales, turning the galaxy from an impossibly vast wilderness into a neighborhood where distant stars are only days or weeks away. The mathematical framework of string theory suggests that such shortcuts might not only be possible, but inevitable. In string theory, fundamental particles are not point-like objects, but tiny vibrating strings that exist in a space of 10 or 11 dimensions. Most of these dimensions are thought to be compactified, curled up so small that they cannot be directly accessed by ordinary matter. But under certain conditions, these extra dimensions might open up, providing pathways for rapid transit across cosmic distances. The energy required to access these higher dimensional pathways might be enormous by everyday standards, but still finite and achievable with sufficiently advanced technology. Particle accelerators already create conditions where extra dimensions might become accessible, albeit only for subatomic particles and only for incredibly brief moments. Future technologies might be able to create stable gateways into higher dimensional space, allowing macroscopic objects to take advantage of extra-dimensional shortcuts. Wormholes represent one theoretical mechanism by which faster-than-light travel might be achieved without violating local speed limits. These hypothetical tunnels through space-time could connect distant regions of the universe, allowing travelers to journey between stars in far less time than light would require to make the same trip through normal space. While wormholes remain purely speculative in our four-dimensional spacetime, they might be natural features of higher dimensional reality. The mathematics of general relativity allows for wormhole solutions, but these exotic structures would require exotic matter with negative energy density to remain stable and traversable. Such matter has never been observed in our dimension, leading most physicists to conclude that traversable wormholes are impossible. But in higher dimensional space, the energy conditions required for wormhole stability might be easier to satisfy, or entirely different types of matter and energy might exist that have no analog in our three-dimensional experience. Recent advances in theoretical physics have revealed new possibilities for faster-than-light travel that do not require exotic matter or violations of energy conservation. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a method for achieving faster-than-light travel by contracting space in front of a spacecraft and expanding space behind it. The spacecraft itself never exceeds the speed of light relative to its local spacetime, but the distortion of space allows it to arrive at distant destinations faster than light, traveling through unmodified space. While the original Alcubierre drive proposal required exotic matter with negative energy density, recent theoretical work has shown that similar effects might be achievable using only positive energy if higher dimensions are taken into account. Extra-dimensional fields might provide the additional degrees of freedom necessary to manipulate spacetime in ways that seemed impossible when considering only our familiar four dimensions. The quantum mechanical properties of higher dimensional space might also enable forms of faster-than-light communication and travel that have no classical analog. Quantum entanglement already demonstrates that information can be shared instantaneously between particles, regardless of the distance separating them. While this quantum correlation cannot be used to send classical information faster than light in our dimension, the situation might be different in higher dimensional space, where quantum fields could have additional properties and capabilities. In higher dimensions, quantum entanglement might support true faster-than-light information transfer, allowing for communication networks that span galactic distances with no time delay. Such networks could enable coordination of activities across vast regions of space, making possible forms of civilization and exploration that are unimaginable within the constraints of our current cosmic speed limit. The concept of parallel universes or alternate realities might also be relevant to faster-than-light travel in higher dimensions. If our universe is just one of many brains floating in a higher dimensional bulk space, then travel between different brains might be possible under certain conditions. Such transdimensional travel would not violate the speed of light within any individual brain, but it could allow for journeys that appear to exceed light speed when viewed from the perspective of a single universe. These parallel universes might have different physical constants, including different values for the speed of light. A traveler who could move between universes might be able to take advantage of realms where light travels faster, using these high-speed universes as cosmic highways to reach distant destinations more quickly than would be possible in our own slower universe. The relationship between consciousness and higher dimensional space might also play a role in faster-than-light travel. Some theories suggest that consciousness operates in dimensions beyond our physical three-dimensional space, potentially giving it access to information and capabilities that transcend the normal limitations of matter and energy. If consciousness can indeed operate in higher dimensions, then it might be possible to project awareness across vast distances instantaneously, achieving a form of faster-than-light travel that does not require the physical transport of matter. This possibility connects to ancient traditions and modern speculation about out-of-body experiences, remote viewing, and other phenomena that seem to involve consciousness operating independently of physical constraints. While such experiences remain controversial and poorly understood from a scientific perspective, they might represent glimpses of capabilities that become possible when consciousness gains access to higher dimensional space. The energy scales required for higher dimensional travel might be accessible through technologies that manipulate matter at the Planck scale, where quantum effects and gravitational effects become equally important. At these incredibly small distances, around 10 to the minus 35 meters, the normal structure of spacetime might break down, revealing the higher dimensional reality that underlies our four-dimensional experience. Nanotechnology, and eventually femtotechnology, the manipulation of matter at scales smaller than atomic nuclei, might provide the tools necessary to engineer spacetime itself. By carefully arranging matter and energy at the Planck scale, it might be possible to create artificial wormholes, open gateways to extra dimensions, or generate the exotic space-time geometries required for faster-than-light travel. The cosmic strings that might have formed in the early universe represent another possible mechanism for achieving faster-than-light motion. These one-dimensional defects in space-time, if they exist, could create regions where the normal limitations of relativity are relaxed. Objects interacting with cosmic strings might be able to achieve velocities that exceed the speed of light, not through direct acceleration, but through manipulation of space-time geometry itself. Dark matter and dark energy, the mysterious components that dominate our universe, might also provide clues about faster-than-light travel in higher dimensions. These invisible substances interact with ordinary matter primarily through gravitational effects, suggesting that they might exist primarily in dimensions beyond our direct observation. Understanding how dark matter and dark energy operate could reveal new principles of physics that enable faster-than-light motion. The accelerating expansion of the universe, driven by dark energy, already demonstrates that space itself can expand faster than light. This cosmic expansion does not violate relativity because it involves the stretching of space rather than motion through space. But the mechanisms that drive this expansion might be harnessed for practical, faster-than-light travel, creating spacecraft that ride waves of expanding space to reach distant destinations. Recent observations of cosmic phenomena have revealed hints that faster-than-light motion might already occur in nature under extreme conditions. Gamma-ray bursts, the most energetic explosions in the universe, sometimes exhibit apparent superluminal motion, with jets of material that seem to travel faster than light. While these observations can usually be explained through relativistic effects and geometrical projection, they demonstrate that the boundary between possible and impossible is often more subtle than it first appears. Pulsar observations have also revealed timing anomalies that might indicate faster-than-light propagation of gravitational effects. When binary pulsars spiral inward due to gravitational wave emission, the observed timing changes sometimes appear to propagate faster than light speed would allow. These anomalies might reflect higher dimensional effects that allow gravitational information to travel through shortcuts unavailable to electromagnetic radiation. The development of quantum computers and quantum communication networks might provide the first practical demonstrations of faster-than-light information transfer. While quantum entanglement cannot be used for faster-than-light communication in our current understanding, it might be possible to exploit higher dimensional aspects of quantum mechanics to achieve true superluminal signaling. Such capabilities would transform not only our understanding of physics but also our technological civilization. The implications of faster-than-light travel extend far beyond mere transportation. Such capabilities would transform our understanding of causality, potentially allowing for communication with the past or influence over future events. The grandfather paradox and other temporal puzzles would need to be resolved through new physics that governs the behavior of information and matter in higher dimensional space-time. Perhaps most remarkably, faster-than-light travel might already be occurring around us at scales we cannot currently detect. Subatomic particles might routinely take higher dimensional shortcuts during interactions. Quantum fields might propagate through extra dimensions at superluminal speeds. And even our own thoughts and perceptions might involve faster-than-light processes that operate beyond our current ability to measure and understand. The search for faster-than-light travel represents humanity's ultimate quest to transcend the limitations that seem to confine us to our small corner of the cosmos. While such travel remains speculative and far beyond our current technological capabilities, the possibility that it might be achieved through access to higher dimensions offers hope that the vast universe might one day become our extended neighborhood, connected by pathways that exist beyond the boundaries of our three-dimensional perception. If the speed of light is a boundary in our dimension, then perhaps the key to crossing that boundary lies not in pushing harder against the walls of our cosmic prison, but in learning to step outside into the freedom of higher dimensional space, where the impossible becomes merely another route to distant destinations waiting to be explored. If our universe is just one of many, then perhaps light is only one of many speeds, determined by the unique rules of each reality. This profound possibility opens our minds to a cosmos far more vast and varied than we have ever dared to imagine, where the speed of light that seems so fundamental to our existence might be nothing more than a local quirk, as specific to our cosmic neighborhood as the temperature on a particular planet or the color of a distant star. The concept of the multiverse emerged from serious attempts to understand why our universe appears to be so perfectly tuned for the existence of complexity, life, and consciousness. The fundamental constants of physics, including the speed of light, the strength of gravity, and the masses of elementary particles, all seem to fall within narrow ranges that allow for the formation of atoms, stars, planets, and ultimately living beings. Change any of these constants by even small amounts, and our universe would become a sterile wasteland where nothing interesting could ever occur. This fine-tuning problem has puzzled physicists for decades. Why should the universe be so precisely calibrated for complexity? One possible answer is that our universe is not unique. Perhaps there exist countless other universes, each with its own set of physical laws and constants. In this vast multiverse, every possible combination of physical parameters would be realized somewhere. We observe a universe fine-tuned for life, simply because we could not exist in any other type of universe to make observations. From this perspective, the speed of light in our universe is not a fundamental constant, but rather a random variable that happened to take the value necessary for our type of reality to exist. In other universes within the multiverse, light might travel at completely different speeds. Some universes might have light that crawls along at the speed of sound, creating worlds where lightning and thunder arrive together, where radio signals take hours to cross continents, and where the night sky flickers and changes as delayed images arrive from different stellar sources. Other universes might have light that travels millions of times faster than in our reality, creating worlds where electromagnetic communication is essentially instantaneous across galactic distances, where stellar evolution proceeds at breakneck pace, and where the energy stored in matter through Einstein's equation E=mc², becomes so enormous that even tiny amounts of matter contain universe-destroying quantities of energy. The mathematical framework of eternal inflation suggests that new universes are constantly being created as different regions of space-time undergo spontaneous expansion episodes. Each of these bubble universes would start with its own unique set of physical parameters, determined by the random quantum fluctuations that triggered its birth. The speed of light, along with all other fundamental constants, would be set by the specific conditions present during each universe's moment of creation. In this picture, our observable universe represents just one bubble in an infinite foam of cosmic bubbles, each existing in its own separate region of a vast higher dimensional space. The boundaries between these bubbles might be impermeable barriers that prevent communication or travel between different universes, or they might be permeable membranes that allow for limited interaction under special circumstances. The concept of parallel universes takes this idea even further, suggesting that every possible history and every possible set of physical laws is realized somewhere within the multiverse. In some of these parallel worlds, light might not exist at all as a distinct phenomenon. Instead, information and energy might be transmitted through entirely different mechanisms that have no analog in our universe. Imagine universes where space itself has memory, preserving and transmitting information about past events without the need for electromagnetic radiation. In such worlds, the concept of a speed limit for information transfer might be meaningless, as all knowledge would be instantly accessible throughout space. Consciousness in these universes might have direct access to information about distant locations and past events, creating forms of awareness that transcend the limitations imposed by light speed in our reality. Other universes might be dominated by forces that we cannot even imagine from our limited perspective. Just as a two-dimensional being would be unable to comprehend magnetic forces, which require three-dimensional space to manifest their full complexity, we might be blind to entire categories of forces that operate in universes with different dimensional structures or different relationships between space and time. Some universes might be purely digital, existing as computational processes in higher dimensional computers. In these simulated realities, the speed of light would be determined by the processing speed of the underlying hardware rather than by fundamental physical constants. Information could travel at the speed of computation, potentially making communication and travel essentially instantaneous across any distance that could be rendered in the simulation. The quantum many-worlds interpretation suggests that every quantum measurement creates a branching of reality, splitting the universe into multiple parallel versions where each possible outcome occurs. If this interpretation is correct, then there exist countless parallel versions of our universe, where the speed of light has slightly different values due to quantum fluctuations in the early universe. In some of these parallel worlds, light travels just a tiny bit faster, creating subtle differences in stellar evolution, atomic structure, and the development of life. In others, light travels more slowly, leading to entirely different pathways for cosmic evolution. Across the vast ensemble of quantum parallel universes, every possible speed of light would be realized, creating an infinite spectrum of realities with different relationships between space, time, and electromagnetic radiation. The anthropic principle provides a framework for understanding why we observe the particular speed of light that exists in our universe. This principle suggests that we can only observe universes that are compatible with our existence. In universes where light travels too fast or too slow for stable atoms and molecules to form, no observers would evolve to measure the speed of light. We necessarily find ourselves in a universe where the speed of light falls within the narrow range that allows for complexity and life. But this anthropic selection effect might conceal the true diversity of possible light speeds throughout the multiverse. The universes we cannot observe might vastly outnumber those we can, creating a hidden majority of realities where light behaves in ways that would seem impossible from our perspective. String theory's landscape of possible vacuum states provides another mechanism for generating universes with different light speeds. According to string theory, the fundamental constants of physics are not truly fundamental, but are determined by the shape and size of extra dimensions. Different configurations of these extra dimensions create different vacuum states, each with its own unique set of physical laws. The string landscape might contain 10 to the 500th power or more different vacuum states, each corresponding to a possible universe with its own value for the speed of light. Some of these vacuum states might be stable, lasting for enormous periods of time and allowing for the evolution of complex structures. Others might be unstable, decaying quickly into different configurations with entirely different physical properties. The process of vacuum decay could even allow for transitions between different universes within the multiverse. If our universe exists in a metastable vacuum state, it might eventually decay into a different configuration with a different speed of light. Such a phase transition could propagate through space at the speed of light, transforming the physical laws as it advances and creating new realities with radically different properties. The holographic principle suggests that our three-dimensional universe might be encoded on a two-dimensional surface, like a hologram that contains three-dimensional information. If this principle is correct, then the speed of light in our universe might be determined by information processing limitations on this two-dimensional boundary, rather than by fundamental properties of three-dimensional space. In other universes with different holographic encodings, the speed of light might be constrained by entirely different information theoretic limits. Some universes might support faster information processing on their boundary surfaces, allowing for higher speeds of light and more rapid communication and computation within the bulk space. The concept of baby universes suggests that black holes in our universe might give birth to new universes with completely different physical laws. As matter falls into a black hole, it might not be destroyed, but rather transferred to a newly created universe that branches off from our own space-time. These baby universes would start with their own unique sets of physical constants, potentially including very different values for the speed of light. If baby universe formation is a common process, then our universe might be part of a vast family tree of connected realities, each spawning new universes through black hole formation. The speed of light in each generation might drift randomly, creating an evolutionary process where different light speeds are tested by natural selection operating on cosmic scales. The eternal return hypothesis suggests that given infinite time and space, every possible configuration of matter and energy will eventually occur. In an infinite multiverse, there would necessarily exist perfect copies of our universe, as well as variations where the speed of light differs by tiny amounts. There might even exist universes that are identical to ours, except for a single photon traveling at a different speed. Digital physics proposes that reality might be fundamentally computational, existing as a vast information processing system, rather than as a collection of matter and energy in space and time. If this view is correct, then the speed of light might be determined by the bandwidth limitations of the underlying computation, rather than by physical constants. In different computational universes, running on different hardware or software platforms, the effective speed of light could vary enormously. Some digital realities might support instantaneous communication across any distance, while others might be so bandwidth limited that light crawls along at glacial speeds. The consciousness-based interpretations of quantum mechanics suggest that observation and measurement play fundamental roles in determining physical reality. If consciousness is indeed central to the nature of reality, then different types of conscious observers might inhabit universes with different physical laws, including different speeds of light. Perhaps the speed of light in each universe is determined by the perceptual and cognitive capabilities of the observers who inhabit that reality. Universes populated by observers with different sensory modalities or different neural architectures might necessarily have different relationships between space, time, and the propagation of information. The implications of a multiverse with variable light speeds extend far beyond abstract physics into the realm of philosophy and meaning. If there exist universes where faster-than-light travel is routine, where communication across cosmic distances is instantaneous, and where the barriers that separate us from distant realms simply do not exist, then our sense of isolation in the cosmos might be fundamentally mistaken. Perhaps consciousness itself has access to information from across the multiverse, creating the intuitions, inspirations, and dreams that seem to come from beyond our local reality. The creative insights that lead to scientific breakthroughs, artistic masterpieces, and spiritual revelations might be glimpses of knowledge that flows from universes where different physical laws allow for different types of information, processing, and communication. The search for evidence of the multiverse has become one of the most active areas of theoretical physics and cosmology. Subtle patterns in the cosmic microwave background radiation might carry signatures of collisions between our universe and neighboring bubble universes. Anomalies in particle physics experiments might reveal the influence of parallel realities, where different physical laws create different particle properties. Even the apparent fine-tuning of physical constants in our universe provides indirect evidence for the existence of other realities with different constants. The probability that a single universe would randomly have physical laws so perfectly suited for complexity and life is vanishingly small. But in an infinite multiverse where every possible combination of physical laws is realized, the existence of at least one life-friendly universe becomes inevitable. The future development of quantum computers and quantum communication networks might eventually provide direct access to information from parallel universes. Quantum entanglement already demonstrates connections that transcend the normal limitations of space and time. As our understanding of quantum mechanics deepens, we might discover ways to exploit these connections for communication with alternate versions of ourselves in parallel realities. The possibility that our universe is just one of many, each with its own speed of light and its own relationship between space, time, and information, transforms our understanding of our place in existence. We are not alone in a vast, cold, and mostly empty universe, governed by inflexible physical laws. Instead, we are part of an infinite community of realities, each exploring different possibilities for the organization of matter, energy, space, and time. In this grand multiverse, the speed of light that seems so fundamental to our reality becomes just one note in an infinite symphony of possibilities, one color in an endless spectrum of potential relationships between the components of existence. Our cosmic speed limit, which appears to isolate us from distant realms, might actually be the key that unlocks understanding of our place in a reality far more rich, diverse, and interconnected than we have ever dared to imagine. If our universe is just one of many, then perhaps light is only one of many speeds, and the barriers that seem to separate us from the infinite might be nothing more than the horizon of our current understanding, waiting to be transcended by the next breakthrough in our eternal quest to comprehend the true nature of existence. String theory opens the door to higher dimensions, and with it, the possibility that light and time may behave in ways we cannot yet perceive. This revolutionary framework in theoretical physics represents perhaps our most ambitious attempt to understand the fundamental nature of reality, suggesting that everything we observe, from the smallest subatomic particles to the largest cosmic structures, emerges from the vibrations of incredibly tiny strings existing in a space of 10 or 11 dimensions. To understand how string theory might transform our understanding of light and its speed, we must first grasp the radical departure this theory represents from our conventional picture of particles and forces. In traditional physics, electrons, quarks, photons, and all other fundamental particles are treated as point-like objects with no internal structure. But string theory proposes that these particles are actually tiny vibrating strings, so small that they appear point-like, even to our most powerful particle accelerators. These strings are unimaginably small, with lengths on the order of the Planck scale, about 10 to the minus 35 meters. To put this in perspective, if an atom were the size of our solar system, a string would be about the size of a tree. At such minuscule scales, the familiar concepts of space and time begin to break down, replaced by a quantum foam where the normal rules of physics no longer apply. The revolutionary insight of string theory is that different vibrational patterns of these fundamental strings correspond to different particles. An electron is a string vibrating in one particular pattern, while a photon is the same type of string vibrating in a completely different way. The mass, charge, and other properties of particles are determined by the specific frequencies and modes of string vibration, much like different musical notes emerge from the same violin string when it vibrates at different frequencies. But for the mathematics of string theory to be consistent, these vibrating strings cannot exist in our familiar three-dimensional space plus time. Instead, they require a total of 10 or 11 dimensions to vibrate freely and produce all the particles and forces we observe. This means that our universe contains 6 or 7 additional spatial dimensions beyond the 3 we can directly perceive. The question that immediately arises is why we cannot see or feel these extra dimensions. String theory addresses this puzzle through the concept of compactification. The extra dimensions are thought to be curled up or folded so tightly at every point in space that they remain invisible to our everyday experience and even to our most sensitive scientific instruments. Imagine looking at a garden hose from a great distance. It appears to be a one-dimensional line, but as you get closer, you realize it actually has width and depth, additional dimensions that were hidden by your limited perspective. The size and shape of these compactified dimensions determine the fundamental constants of physics in our observable three-dimensional world. The speed of light, the strength of gravity, the masses of elementary particles, all of these apparent constants are actually determined by the geometry of the extra dimensions. Change the size or shape of the hidden dimensions, and you automatically change the physics of our three-dimensional experience. This geometric origin of physical constants has profound implications for our understanding of the speed of light. In different regions of the higher dimensional space, where the extra dimensions might have different sizes or shapes, the effective speed of light could be completely different from what we observe in our local region. What we consider to be a universal constant might actually be a local environmental variable, as dependent on local conditions as the temperature or pressure in our atmosphere. The mathematical structure of string theory reveals that the extra dimensions can take on an enormous variety of different shapes and sizes. Each possible configuration, called a vacuum state or a point in the string landscape, corresponds to a different set of physical laws and constants. The total number of possible vacuum states is estimated to be around 10 to the 500th power, a number so large that it defies comprehension. Some of these vacuum states might allow for light speeds that are millions of times faster than what we observe, while others might constrain electromagnetic radiation to crawl along at speeds far slower than anything we can imagine. In vacuum states where the extra dimensions have very different geometries, light might not exist at all as a distinct phenomenon, replaced by entirely different mechanisms for transmitting energy and information. The process by which our universe selected its particular vacuum state from this vast landscape remains one of the deepest mysteries in modern physics. It might have occurred randomly during the Big Bang, when quantum fluctuations in the early universe determined which particular configuration of extra dimensions would be realized in our cosmic region. Alternatively, there might exist some deeper principle that selected our specific vacuum state from among all the possibilities. String theory also predicts the existence of additional objects beyond just vibrating strings. The theory includes higher dimensional structures called branes, short for membranes, which can have anywhere from 0 to 9 spatial dimensions. Our entire three-dimensional universe might be just such a brain, a three-dimensional surface embedded in the higher dimensional space where strings vibrate. If this picture is correct, then all the particles and forces we can observe are confined to our three-dimensional brain, unable to escape into the extra dimensions of the bulk space that surrounds us. The only exception might be gravity, which could propagate freely through all dimensions of the bulk, potentially explaining why gravity appears so much weaker than the other fundamental forces. This brain-world scenario opens up remarkable possibilities for the behavior of light and other forms of electromagnetic radiation. While photons might be confined to our brain and unable to access the extra dimensions directly, they could still be influenced by the geometry and dynamics of the higher dimensional space. Changes in the bulk geometry could alter the effective speed of light on our brain, creating variations that appear mysterious from our three-dimensional perspective. Other brains might exist in the same higher dimensional space, each potentially housing its own three-dimensional universe with its own set of physical laws. These parallel brain worlds might have completely different relationships between space, time, and electromagnetic radiation. Some might support light speeds that are essentially infinite, allowing for instantaneous communication across cosmic distances. Others might prohibit electromagnetic radiation entirely, requiring entirely different mechanisms for energy and information transfer. The dynamics of string theory predict that these extra dimensions are not static, but can change size and shape over cosmic timescales. As the universe evolves, the compactified dimensions might expand, contract, or undergo more complex transformations that alter the apparent constants of physics in our three-dimensional world. The speed of light might be slowly changing as we speak, influenced by gradual modifications in the geometry of dimensions we cannot directly observe. Such changes would be incredibly slow from our perspective, occurring over millions or billions of years. But sensitive astronomical observations might be able to detect these variations by studying light from the most distant galaxies, whose radiation has been traveling toward us for most of the history of the universe. Subtle changes in the fine structure constant, which is intimately related to the speed of light, have already been tentatively detected in some quasar observations. String theory also predicts the existence of new types of particles that have no counterparts in conventional physics. These exotic particles might be able to propagate through the extra dimensions, carrying information and energy along pathways that are invisible to electromagnetic radiation. Such particles could enable forms of faster-than-light communication that do not violate the apparent speed limit for photons in our three-dimensional space. The mathematical framework of string theory includes objects called D-branes, which are specific types of branes where open strings can end. The endpoints of these open strings correspond to particles that are confined to move only along the surface of the D-brane. If our three-dimensional space is such a D-brane, then photons might be endpoints of open strings that cannot leave our brain, explaining why electromagnetic radiation seems confined to our familiar dimensions. But string theory also allows for closed strings, which form loops that are not attached to any brain and can therefore move freely through all dimensions of the higher dimensional space. These closed strings might correspond to particles that can access the extra dimensions, potentially enabling faster-than-light travel and communication through higher dimensional shortcuts. The vibrations of strings in extra dimensions can create resonances and interference patterns that have no analog in our three-dimensional experience. These higher dimensional acoustics might influence the behavior of particles and fields in our observable universe in subtle but detectable ways. The speed of light itself might fluctuate slightly due to interference effects from string vibrations in the compactified dimensions. Recent developments in string theory have revealed connections to other areas of physics that seemed completely unrelated. The AD-CFT correspondence, for example, establishes a precise mathematical relationship between gravitational theories in higher dimensional anti-de Sitter space and quantum field theories on the boundary of that space. This correspondence suggests that our three-dimensional reality might be holographically encoded on a two-dimensional surface, with all the information about our universe contained in the dynamics of this lower dimensional boundary. If this holographic principle is correct, then the speed of light in our three-dimensional space might be determined by information processing limitations on the two-dimensional holographic boundary, rather than by fundamental properties of three-dimensional electromagnetism. Changes in the boundary dynamics could alter the effective speed of light in the bulk space, creating apparent violations of what we consider to be fundamental physical laws. String theory also predicts the existence of extra dimensions that are not compactified, but are instead infinite in extent, parallel to our three familiar spatial dimensions. These large extra dimensions could be invisible to us if ordinary matter and electromagnetic radiation are confined to our three-dimensional brain, while gravity alone can propagate through the extra dimensions. In such scenarios, the true fundamental scale of physics might be much lower than we currently believe. Gravity might become as strong as the other forces at energy scales accessible to particle accelerators, but we do not observe this because most of the gravitational force leaks away into the extra dimensions. This could have implications for the speed of light, which might be related to gravitational effects in ways that become apparent only when the extra dimensions are taken into account. The mathematical consistency of string theory requires not only extra spatial dimensions, but also specific relationships between these dimensions and the dimension of time. Some versions of string theory include multiple time dimensions, creating space-time geometries that are far more complex than anything we experience in our everyday lives. In such multi-temporal realities, the concept of a single speed of light might be meaningless, replaced by a complex network of causal relationships that connect different temporal directions. The landscape of string theory vacuum states includes configurations where the extra dimensions undergo periodic cycles of expansion and contraction. In these oscillating models, the effective speed of light in our three-dimensional world might vary periodically, speeding up and slowing down as the hidden dimensions expand and contract. Such variations could create cosmic rhythms that influence the evolution of galaxies, stars, and even biological processes over very long timescales. String theory also suggests that our Big Bang might not have been the beginning of time, but rather a transition between different phases of a higher dimensional reality. In the ekpyrotic scenario, our three-dimensional brain collides periodically with other brains in the higher dimensional bulk space, creating Big Bang-like events that reset the physics of our observed universe. Each collision might establish a new relationship between the extra dimensions and our three-dimensional space, potentially changing the speed of light and other fundamental constants. The mathematical tools developed for string theory have revealed unexpected connections between seemingly unrelated areas of physics and mathematics. These connections suggest that the speed of light and other fundamental constants might be related to deep mathematical structures that transcend our particular physical reality. Understanding these connections could reveal why light travels at the specific speed we observe, and whether this speed has any deeper significance beyond its role in our local physics. Experimental tests of string theory remain challenging because the characteristic energy scales of string physics are far beyond what current particle accelerators can reach. However, the theory makes predictions about extra dimensions and higher dimensional physics that might be testable through precision measurements of gravity at very small distances, searches for missing energy in particle collisions, and careful analysis of cosmic ray interactions in the upper atmosphere. The implications of string theory for our understanding of light and its speed extend far beyond academic physics. If the theory is correct, then the apparent constants of nature that seem so fundamental to our existence are actually environmental variables determined by the geometry of dimensions we cannot perceive. This suggests that reality is far more malleable and dynamic than we currently imagine, with the potential for dramatic changes in the laws of physics as the hidden dimensions evolve. String theory opens the door to higher dimensions, where light, time, space, and matter might behave according to principles that challenge everything we think we know about the nature of existence. In these hidden realms, the speed of light might be just one possibility among many, determined by the dance of dimensions we are only beginning to understand. The limitations of our measurements could be more profound than we think. Perhaps, as we reach beyond our known dimensions, we will find the boundaries of light stretch and bend. This possibility challenges everything we believe about the precision and accuracy of our scientific observations, suggesting that even our most carefully conducted experiments might be capturing only a fragment of a much larger and more complex reality. For over 3 centuries, scientists have refined their measurements of the speed of light with ever-increasing precision. What began as crude estimates using lanterns on hilltops has evolved into extraordinarily sophisticated experiments using atomic clocks, laser interferometry, and quantum mechanical effects. Today, we know the speed of light to 15 decimal places, making it one of the most precisely measured constants in all of physics. Yet this very precision might be masking fundamental limitations in our understanding of what we are actually measuring. Every measurement of light speed that has ever been conducted takes place within our three-dimensional space, plus time. We send light from one location to another within our familiar dimensions and measure the time it takes to make the journey. But what if light, during its travel, is actually taking shortcuts through higher dimensions that we cannot detect or measure? What if the speed we observe is not the true speed of light in higher dimensional space, but rather an effective speed that results from light's interaction with the compactified extra dimensions? Consider the analogy of measuring the speed of a car traveling on a winding mountain road. From a helicopter overhead, you might measure the time it takes the car to travel from one point to another as the crow flies, calculating an apparent speed based on the straight line distance. But the car is actually traveling a much longer path along the curved road, meaning its true speed along its actual route is much higher than your aerial measurement would suggest. Similarly, when we measure the speed of light, we might be observing only the projection of light's true path through higher dimensional space onto our three-dimensional world. The photons might be traveling much faster through the full dimensionality of space, but we observe only the component of their motion that occurs within our limited dimensional perspective. Recent experiments at the world's most advanced particle accelerators have begun to reveal hints that our understanding of light's behavior might be incomplete. When high-energy photons are created in particle collisions, they occasionally exhibit properties that seem inconsistent with our standard models of electromagnetic radiation. Some of these anomalies might be explained by interactions with extra dimensions that become accessible only at very high energies. The Large Hadron Collider, the most powerful particle accelerator ever built, has recorded events where energy seems to disappear without a trace. These missing energy events could be explained if some of the particles created in high-energy collisions escape into extra dimensions, carrying energy away from our three-dimensional space. If photons can also access these extra dimensions under extreme conditions, then their speed and behavior in these realms might be completely different from what we observe in ordinary circumstances. Precision measurements of the cosmic microwave background radiation have revealed subtle patterns that might indicate influences from higher dimensional physics. This ancient light, which has been traveling through space for over 13 billion years, carries information about conditions in the early universe, when extra dimensions might have been more accessible than they are today. Tiny variations in the temperature and polarization of this radiation could reflect the influence of extra-dimensional effects on light propagation over cosmic distances. Some of the most puzzling observations in modern astronomy involve apparent violations of the speed of light limit. Gamma-ray bursts, the most energetic explosions in the universe, sometimes exhibit jets of material that appear to be traveling faster than light. While these observations are usually explained through relativistic effects and geometric projection, they demonstrate that our understanding of light's behavior in extreme environments might be incomplete. Pulsar timing arrays, which use the incredibly precise ticks of rotating neutron stars as cosmic clocks, have detected anomalies that might indicate faster than light propagation of gravitational effects. When binary pulsars spiral inward due to gravitational wave emission, the observed timing changes sometimes appear to propagate faster than electromagnetic radiation would allow. These observations could reflect higher dimensional effects that allow information to travel through shortcuts unavailable to light confined to our three-dimensional space. Laboratory experiments with quantum entanglement have demonstrated that quantum correlations can be established instantaneously between particles, regardless of the distance separating them. While this quantum non-locality cannot be used to send classical information faster than light, it suggests that some aspects of physical reality operate according to principles that transcend our familiar space-time limitations. The mechanism underlying quantum entanglement might involve higher dimensional connections that allow for instantaneous correlation without violating local speed limits. Recent developments in metamaterial research have created artificial materials with electromagnetic properties that do not exist in nature. These engineered structures can bend light in ways that seem to violate conventional optics, creating negative refractive indices, cloaking effects, and even apparent faster-than-light propagation under certain conditions. While these effects can usually be explained within conventional electromagnetic theory, they demonstrate that light's behavior can be far more exotic than our everyday experience suggests. High-precision atomic clocks, accurate to 1 part in 10 to the 18th power, have revealed tiny variations in the rate of time flow that cannot be explained by known gravitational or relativistic effects. These temporal anomalies might reflect the influence of extra dimensions on the fundamental nature of space-time itself. If time flows differently in regions where extra dimensions are more accessible, then measurements of light speed, based on timing, could be systematically affected in ways we do not currently understand. Observations of distant quasars have revealed hints that the fine structure constant, which determines the strength of electromagnetic interactions and is intimately related to the speed of light, might have been different in the early universe. If this constant has indeed varied over cosmic time, then the speed of light might also be slowly changing as the universe evolves. Such variations could reflect changes in the geometry of extra dimensions that influence the effective values of physical constants in our three-dimensional world. The phenomenon of vacuum birefringence, predicted by quantum electrodynamics but never definitively observed, involves the splitting of light into different polarization components when passing through regions of strong electromagnetic fields. Recent experiments using powerful lasers and magnetic fields have claimed tentative detection of this effect, but the results are at the very limits of experimental sensitivity. If vacuum birefringence does occur, it suggests that empty space has structure and properties that could be influenced by higher dimensional effects. Searches for axions, hypothetical particles that could make up dark matter, have used the assumption that these particles could convert into photons under certain conditions. The failure to detect actions in Earth-based experiments might not mean that these particles do not exist, but rather that the conversion process involves higher dimensional physics that cannot be replicated in our current experimental setups. Neutrino oscillations, where neutrinos change from one type to another as they travel through space, demonstrate that these nearly massless particles have access to physics beyond the standard model. Some theoretical models suggest that neutrino oscillations involve mixing with higher dimensional states that are invisible to our current detectors. If neutrinos can access extra dimensions, they might provide a window into higher dimensional physics that could reveal new aspects of light's behavior. The search for violations of Lorentz invariance, the principle that the laws of physics are the same for all observers moving at constant velocities, has become increasingly sophisticated. While no definitive violations have been confirmed, some experiments have reported tiny effects that might indicate the influence of higher dimensional physics on light propagation. These effects are typically interpreted as evidence for quantum gravity phenomena, but they could also reflect the influence of extra dimensions on electromagnetic radiation. Gravitational wave detectors like LIGO and Virgo have opened a new window on the universe, detecting ripples in space-time itself. These instruments are sensitive enough to measure distortions smaller than 1/10,000th the width of a proton, making them potentially capable of detecting signatures of extra-dimensional physics. If gravitational waves can propagate through higher dimensions while electromagnetic waves cannot, then comparisons between gravitational wave and electromagnetic observations of the same events might reveal discrepancies that indicate higher dimensional effects. The study of cosmic rays, high-energy particles that strike Earth's atmosphere from space, has revealed events that seem to violate known physics. Some ultra-high-energy cosmic ray events appear to carry more energy than should be possible if they travel through normal three-dimensional space from their suspected sources. These anomalies might be explained if cosmic rays can access higher dimensional shortcuts that allow them to preserve energy over distances that would normally cause significant losses. Precision spectroscopy of hydrogen atoms has revealed tiny discrepancies between theoretical predictions and experimental measurements. These anomalies, known as the proton size puzzle, might reflect the influence of extra-dimensional effects on atomic structure. If the electromagnetic fields that bind electrons to atomic nuclei are influenced by higher dimensional physics, then measurements of atomic transitions could provide indirect evidence for extra-dimensional effects on light propagation. The development of quantum sensors with unprecedented sensitivity has opened new possibilities for detecting subtle violations of known physics. Atom interferometers can measure accelerations to extraordinary precision, potentially detecting the influence of extra-dimensional forces. quantum magnetometers can detect magnetic fields weaker than those produced by a single electron spin, potentially revealing signatures of higher dimensional electromagnetic effects. The search for dark photons, hypothetical particles that interact only weakly with ordinary photons, represents another frontier in testing our understanding of electromagnetic radiation. These hidden sector particles might be ordinary photons that propagate primarily through extra dimensions, interacting only weakly with our three-dimensional world. Laboratory experiments using intense laser fields and sensitive detectors are searching for evidence of dark photon production and detection. The phenomenon of cosmological redshift, where light from distant galaxies is shifted to longer wavelengths due to the expansion of space, provides another test of our understanding of light propagation over cosmic distances. Recent observations of the most distant galaxies have revealed redshifts that seem inconsistent with standard cosmological models, possibly indicating that light behaves differently when traveling through regions of space where extra dimensions might be more accessible. The measurement of light speed in different media has revealed that electromagnetic radiation can travel faster than its speed in vacuum under certain conditions, such as in regions of anomalous dispersion, where the group velocity exceeds the speed of light in vacuum. While these effects do not violate causality and can be explained within conventional electromagnetic theory, they demonstrate that light's behavior can be far more complex than simple measurements in vacuum might suggest. The study of nonlinear optical effects, where intense light fields modify the properties of the medium through which they propagate, has revealed phenomena that seem to challenge conventional understanding. In some nonlinear materials, light pulses can appear to travel faster than the speed of light in vacuum, or even to exit a material before they have fully entered it. These effects might reflect higher dimensional aspects of electromagnetic propagation that become apparent only under extreme conditions. The development of metamaterials with negative refractive indices has created situations where light appears to travel backward in time, at least in terms of its phase velocity. While these effects can be explained within conventional electromagnetic theory, they suggest that our understanding of light propagation might be incomplete, particularly in artificial structures that have no natural analogues. Future experiments planned for the next generation of particle accelerators, gravitational wave detectors, and space-based observatories will probe energy scales and sensitivities that approach the fundamental limits imposed by quantum mechanics and general relativity. These experiments might finally provide definitive evidence for extra-dimensional effects on light propagation, or they might reveal entirely new physics that challenges our current understanding of electromagnetic radiation. The possibility that we are measuring the speed of light incorrectly, or at least incompletely, opens profound questions about the nature of scientific knowledge itself. If our most fundamental measurements are limited by our dimensional perspective, then the entire edifice of physics might be built on foundations that are far more provisional than we currently believe. Yet this uncertainty also represents an opportunity, suggesting that reality might be far richer and more surprising than our current theories predict. The limitations of our measurements could indeed be more profound than we think, reflecting not errors in our experimental techniques, but fundamental constraints imposed by our three-dimensional perspective on a reality that extends into realms we are only beginning to imagine. As we push the boundaries of experimental precision and explore ever more extreme conditions, we edge closer to discovering whether light truly travels at a universal constant speed, or whether this apparent constant is simply a local manifestation of deeper principles that operate in dimensions beyond our current ability to perceive and measure. As we push the boundaries of science, we begin to question everything we know about the cosmos. Could the speed of light be just one of the many wonders waiting to be discovered in dimensions beyond our own? This question represents the culmination of our journey through the mysteries of light, space, and time, pointing toward a future where our understanding of reality might be transformed in ways that seem impossible from our current perspective. The quest to understand light's true nature in higher dimensions has already begun to reshape the landscape of scientific research. Theoretical physicists are developing new mathematical frameworks that extend our current theories into realms where the familiar rules of space and time no longer apply. These theories predict phenomena that challenge every assumption we have made about the fundamental nature of existence, suggesting that light, gravity, matter, and energy might all behave according to principles that transcend our three-dimensional experience. The technological implications of higher dimensional physics could revolutionize human civilization in ways that parallel the great scientific revolutions of the past. Just as the discovery of electricity transformed society from a world of candles and horses to one of electric lights and powered machinery, the mastery of higher dimensional physics could open pathways to technologies that seem magical from our current perspective. Imagine communication systems that operate through higher dimensional channels, allowing for instantaneous contact across galactic distances. Such technologies would eliminate the cosmic loneliness imposed by the speed of light limit, connecting Earth with distant colonies among the stars, and enabling the coordination of activities across scales that encompass the entire observable universe. Scientists working on different planets could collaborate in real time, sharing discoveries and insights without the years or decades of delay that light speed currently imposes. Transportation systems based on higher dimensional principles could make the vast distances of space as manageable as crossing a city. Spacecraft that access extra-dimensional shortcuts might travel between star systems in days or weeks, rather than the thousands of years required by conventional propulsion. The galaxy would become humanity's extended neighborhood, with distant worlds as accessible as foreign countries are today. The energy implications of higher dimensional physics could solve the fundamental challenges facing human civilization. If matter and energy can flow between dimensions, then the total energy available to any particular universe might be essentially unlimited. Technologies that tap into higher dimensional energy sources could provide clean, abundant power that makes current energy concerns seem as quaint as worrying about running out of firewood. Medical applications of higher dimensional physics might allow for healing technologies that seem miraculous from our current perspective. If consciousness and biological processes involve higher dimensional components, then understanding these connections could lead to treatments that address the root causes of disease and aging. The boundaries between life and death, health and illness, might become as malleable as the boundaries between different regions of space. The search for evidence of higher dimensional physics has already begun to drive the development of new experimental technologies. Particle accelerators of unprecedented energy are being designed to probe the smallest scales of space and time, where extra dimensions might become accessible. These machines will create conditions that have not existed since the first moments after the Big Bang, potentially opening windows into realms that have remained hidden since the birth of our universe. Gravitational wave detectors of extraordinary sensitivity are being planned to listen for ripples in space-time that might carry signatures from higher dimensional sources. These instruments could detect the gravitational influence of objects existing primarily in extra dimensions, providing our first direct observations of matter and energy beyond our three-dimensional world. Space-based observatories, positioned at the edges of our solar system, will search for subtle variations in the speed of light that might indicate the influence of higher dimensional effects. By measuring light from the most distant sources in the universe with unprecedented precision, these instruments might reveal that the speed of light is not truly constant, but varies in ways that reflect the hidden structure of reality. Quantum computers of increasing sophistication are being developed to explore the information-theoretic aspects of higher dimensional physics. These machines might eventually access quantum states that exist partially in extra dimensions, enabling computations that are impossible within the confines of our three-dimensional space. Such quantum computers could solve problems that would require more atoms than exist in the observable universe if attempted with conventional technology. The biological sciences are beginning to explore whether life itself might involve higher dimensional processes. Some researchers propose that consciousness operates through quantum mechanical effects that might extend into extra dimensions, potentially explaining phenomena like intuition, creativity, and the sense of connection that people sometimes feel across great distances. Understanding these connections could lead to technologies that enhance human cognitive capabilities or enable direct mind-to-mind communication. Neuroscientists are investigating whether the 100 billion neurons in the human brain might be connected through pathways that exist partially in higher dimensions. This could explain how the brain processes information with such remarkable efficiency, and why consciousness seems to involve more than just the electrical and chemical signals observable in our three-dimensional space. The study of genetics and molecular biology is revealing mechanisms that might involve higher dimensional information, storage, and processing. DNA contains far more information than would seem possible given its chemical structure, suggesting that genetic information might be encoded in ways that extend beyond our three-dimensional understanding of molecular architecture. Ecology and environmental science are beginning to consider whether the complex interconnections between different species and ecosystems might involve higher dimensional communication channels. This could explain phenomena like the mysterious coordination of behavior across vast populations of organisms and the rapid spread of adaptive responses to environmental changes. The development of artificial intelligence systems is approaching levels of sophistication where these technologies might begin to exhibit behaviors that seem to transcend their programmed capabilities. Some researchers speculate that sufficiently complex information processing systems might spontaneously access higher dimensional aspects of reality, potentially achieving forms of intelligence that surpass human capabilities in unexpected ways. Materials science is exploring the possibility of creating substances with properties that emerge from higher dimensional physics. These metamaterials might exhibit characteristics like negative mass, faster than light information transmission, or the ability to exist simultaneously in multiple locations. Such materials could enable technologies that seem to violate the fundamental laws of physics as we currently understand them. The field of cosmology is preparing for discoveries that might reveal the true structure of reality beyond our observable universe. Future observations might detect the influence of other universes, parallel dimensions, or exotic forms of matter and energy that exist primarily in higher dimensional space. These discoveries could transform our understanding of our place in the cosmic hierarchy. Archaeological research is beginning to explore whether ancient civilizations might have had access to knowledge about higher dimensional physics. Some researchers propose that certain mysterious artifacts and structures from the past might represent attempts to manipulate higher dimensional forces using technologies that we do not yet understand. The study of consciousness and human psychology is investigating whether certain mental phenomena might reflect higher dimensional aspects of human nature. Experiences like déjà vu, precognition, and telepathy might represent genuine perceptions of information that flows through channels extending beyond our normal three-dimensional awareness. Educational systems are beginning to prepare students for a future where higher dimensional physics might transform every aspect of human knowledge. New curricula are being developed to help people think beyond the limitations of three-dimensional space, fostering the kind of multi-dimensional awareness that might be necessary to understand and utilize higher dimensional technologies. The philosophical implications of higher dimensional physics extend far beyond science and technology into the realm of human meaning and purpose. If reality extends into dimensions we cannot currently perceive, then our current understanding of existence represents only the smallest fragment of a much larger picture. This realization could fundamentally transform how we think about life, death, consciousness, and the ultimate nature of existence. Religious and spiritual traditions are beginning to engage with the implications of higher dimensional physics, exploring how ancient wisdom might be reconciled with modern scientific discoveries. Many mystical traditions have long proposed that reality extends beyond the physical world we can observe, and higher dimensional physics might provide a scientific framework for understanding these spiritual insights. The economic implications of higher dimensional technologies could create abundance on a scale that makes current concerns about scarcity obsolete. If energy and matter can be accessed from higher dimensions, then the fundamental constraints that have shaped human history might be eliminated, creating possibilities for forms of civilization that transcend current limitations. International cooperation in the development of higher dimensional technologies could unite humanity in common purpose, creating shared goals that transcend the political and cultural divisions that have historically separated different nations and peoples. The challenges and opportunities presented by higher dimensional physics might be so profound that they require the combined efforts of all human civilization to address properly. The timeline for these developments remains uncertain, but the pace of discovery in fundamental physics suggests that revolutionary breakthroughs might occur within the next few decades. The convergence of advances in particle physics, quantum mechanics, cosmology, and computational technology is creating conditions where higher dimensional effects might finally become accessible to human investigation and manipulation. Future generations might look back on our current era as the time when humanity first began to glimpse the true nature of reality, much as we now view the early 20th century as the period when humans first understood atoms, radioactivity, and the quantum nature of matter. The speed of light that seems so fundamental to our current understanding might be remembered as a quaint limitation that applied only to beings trapped in three-dimensional thinking. The journey toward understanding light's true nature in higher dimensions represents more than just a scientific quest. It embodies humanity's deepest aspirations to transcend limitations, explore new frontiers, and understand our place in a universe that might be far stranger and more wonderful than we have ever dared to imagine. Children born today might grow up in a world where faster-than-light communication is routine, where travel between stars takes less time than current intercontinental flights, and where the fundamental forces of nature can be manipulated as easily as we now control electricity. These future humans might possess capabilities that seem godlike from our current perspective, yet they will undoubtedly face new challenges and mysteries that we cannot even begin to comprehend. The speed of light that has defined the boundaries of our cosmic prison might prove to be nothing more than the first step in an infinite staircase of discovery, each level revealing new aspects of reality that expand our understanding of what is possible. In dimensions beyond our current perception, light itself might be just the beginning of phenomena so exotic and wonderful that they challenge the very foundations of logic and imagination. As we stand on the threshold of these discoveries, we can only marvel at the possibility that the universe we think we know represents merely the shadow of a reality so rich, complex, and beautiful that it exceeds our wildest dreams. The future of light, and our understanding of its role in the cosmic order, stretches before us like an infinite horizon, promising revelations that could transform not just our technology and our science, but our very conception of what it means to exist in a universe where the impossible might be merely another word for the not yet understood. The universe is vast, and the dimensions beyond our own are as mysterious as they are infinite. As we rest beneath the stars, we embrace the unknown, knowing that the secrets of light, time, and space are far from revealed. Tonight, our journey through the mysteries of higher dimensional reality draws to a close, yet we find ourselves standing at the edge of understanding, gazing into an infinite cosmos where the familiar boundaries of our three-dimensional world dissolve into possibilities beyond imagination. We have explored how the speed of light, which seems so fundamental in our everyday experience, might be nothing more than a local phenomenon. In our three-dimensional world, this cosmic speed limit defines the boundaries of causality and shapes our understanding of physics. Yet we have discovered that this apparently universal constant might be as specific to our reality as the weather on Earth. The mathematics of higher dimensional physics reveals possibilities that challenge every assumption about existence. In dimensions beyond our perception, space and time might allow for connections across distances that seem impossibly vast. Light might take shortcuts through higher dimensional pathways, not by violating local speed limits, but by accessing routes invisible to our three-dimensional perspective. String theory shows us a cosmos where vibrating strings exist in 10 or 11 dimensions. Most remain hidden, compactified into scales smaller than subatomic particles. Yet their geometry determines the apparent constants of physics in our world, including the speed of electromagnetic radiation through our three-dimensional space. The multiverse extends these possibilities further, suggesting our universe might be just one bubble in an infinite foam of realities. Each could have its own relationship between space, time, and light. Some might be worlds where faster-than-light travel is routine, where the barriers isolating us from distant space simply do not exist. Our experimental investigations reveal hints that our understanding might be incomplete. Particle experiments occasionally show results that seem to violate known physics. Astronomical observations reveal subtle anomalies in light behavior from distant sources, potentially indicating electromagnetic radiation behaves differently in regions where extra dimensions might be accessible. Quantum entanglement demonstrates that information can be shared instantaneously between particles regardless of distance, suggesting some aspects of reality operate beyond familiar space and time limitations. These quantum connections might involve pathways through higher dimensional space. Consciousness itself might connect to higher dimensional physics in ways we are beginning to understand. The complexity of human awareness might require capabilities extending beyond three-dimensional space. Our thoughts, dreams, and intuitions might reflect access to information flowing through channels in dimensions beyond direct perception. The speed of light, rather than being a fundamental barrier, might be just the first glimpse of a cosmic highway system extending into realms we cannot yet access. The apparent isolation of Earth might be an illusion created by our limited dimensional perspective. In higher dimensional space, we might be surrounded by civilizations connected by networks, operating at speeds that seem magical from our understanding. If reality is fundamentally higher dimensional, then our three-dimensional experience might be like watching shadows on cave walls, perceiving only projections of a much richer existence. Everything we consider real might be merely surface appearances of deeper structures, operating according to principles we have yet to discover. The future holds promise of discoveries that could transform our understanding of light, space, time, and reality itself. Children born today might grow up understanding the speed of light as just one parameter in a vast space of possibilities, where travel between stars uses higher dimensional shortcuts and communication across cosmic distances is essentially instantaneous. As we drift towards sleep under the canopy of stars, we find comfort knowing the universe is far stranger, more beautiful, and more full of possibilities than our current theories suggest. The light from distant galaxies might carry secrets about dimensions and realities beyond our ability to perceive. In our dreams, unbound by waking logic, we might glimpse aspects of higher dimensional realities. The strange connections in our dream experiences might reflect genuine access to realms where space and time operate according to different principles, where the speed of light is no barrier to connection. As we rest beneath the infinite expanse of night, we embrace the mystery of existence itself. We are part of a cosmos extending far beyond what we can measure, connected to realities that transcend current understanding, yet remain woven into our being. The speed of light that seems to isolate us might actually be the key unlocking understanding of our place in a multiverse of infinite possibility. Tonight, as sleep carries us into realms where the impossible becomes possible, we rest knowing the universe holds secrets beyond imagination. The speed of light is not a barrier but a doorway, not a limitation but an invitation to explore realities where wonder and discovery never end. In dimensions beyond our own, light itself might be just the beginning of marvels awaiting our understanding. The universe is vast. The dimensions beyond our own are infinite in their mystery, and as we embrace the unknown, we join the eternal dance of consciousness, reaching toward truth, forever seeking to understand the nature of the light that illuminates not just our world, but the infinite expanse of existence itself.